So this topic work and energy is actually improvisation of Newton's laws. Improvisation of Newton's second law particularly, because we are going to see what is called work energy theorem. We are going to see what is called work energy theorem, which is actually modified form of Newton's second law. So if you take Newton's second law and modify it in certain way, you get what is called work energy theorem. So to understand work energy theorem, first we need to understand work done by a force, what is energy, what are the different types of energy, and all those aspects. That is the idea. So our topic starts with this. First we will try to understand work done by a force. This is our starting point. So let us define this new quantity, work done by a force. The way we are defining it is keeping something in mind at a later stage. All definitions are made by keeping something in mind which will be coming up at a later stage. So you cannot challenge a definition. You can try to define a new quantity in your own way, and if it is useful later, the definition will be accepted. If it can explain the working of nature, the definition will be accepted. So work done by a force is defined as integral F dot ds. I am going into very fundamental definition which is always correct. So work done by a force is defined as integral F dot ds, where ds is displacement of, very important point, displacement of point of application of force. Point of application of force. That means, see, the word point of application, that means if I have some object, let us say the duff with which you make the roti or chapati. Suppose I am applying a force here. You are applying force at this point. So you must take displacement of this point. First of all, this point could have moved in a very complicated path. The duff could have deformed like this when you applied force. So this point could have moved in a very complicated path. You are splitting that path, the total displacement, into little displacement vectors. So this path, I am zooming this. That path you are splitting into small displacement vectors. And the force value, when this displacement is occurring, you take the force value and do dot product with that displacement. And again, for the next displacement, you take force value and do dot product with that displacement. Like that, you take dot product of all displacements and the corresponding forces and add them up, which is integration. So that is giving you work done by that force. So you must take displacement of the point where force is applied, not the whole body, not displacement of the body, displacement of only that point. For example, if I have a chewing gum which is a deformable object, if I am applying force here, you must take displacement of only this point and not the whole chewing gum. The whole chewing gum may move, may not move, I don't care. But if this point moves, then you can define work done by this force as integral F dot ds. So ds is displacement, a small displacement of that point where force is applied. So total displacement you are dividing into small displacements. You are finding each little work done and adding up. So actually this integral F dot ds, what I am saying, it is nothing but F1 dot ds1 plus F2 dot ds2 plus so on. That means the total path you are dividing into small, I should not even say small, infinitely small displacements. Okay, and for every small displacement you find the force value, take dot product, because force could be changing from time to time. So for every small displacement, find force value and take dot product. Add all these. This addition is only what is called integration. So work done by a force, most general definition is integral F dot ds, where ds is displacement of that point where force is applied. This is the most general definition of work done by a force. So let us see some special cases coming out of this, because most general definition we use only very rarely. Most of the time we will be using some special cases. So general definition, you should not forget this. General definition, work done by a force F is given by integral F dot ds, where this is displacement of that point where force is applied. Displacement of that point where force is applied. Now let's go to special cases, because most of the times we'll be encountering these special cases. First case is force is constant force. The force which is being applied on the object, that force is constant force. When a vector is said to be constant, neither its magnitude must change nor its direction must change. So if you say it is a constant force, force magnitude must not change, force direction also must not change. In such a case, work done by this force, which we wrote as F dot ds, which is nothing but sum of terms like this. Now because the force is constant, you can replace this F1, this F2 all with the value F, and when you are adding, you can take F with the dot product common and write it as ds1 plus ds2 plus like that. Because if all these F1, F2, F3 are by F, then you have F dot ds1 plus F dot ds2 plus F dot ds3. Take F dot common, we will have ds1 plus ds2 plus ds3. So indirectly what I am saying, this can be written as F dot integral ds, because you are adding all displacements. So I am doing the same thing here. F is a constant, so you can take F along with dot product outside and you can write integral ds. Because the force is constant, it is not changing in magnitude nor in direction. The proof of how you are writing from this step to this step is there on the previous page. The proof is here. Integral F dot ds is F1 dot ds1 plus F2 dot ds2, so on. But if this F1, F2, F3 are always the same, they are never changing, you can take it out and write F dot ds1 plus ds2. So you can write as F dot integral ds. So if F is constant, if it is not changing, you can take it out with dot product and write integral ds bar. And when you add all displacements, small displacements vectorially, you will get the net displacement. Now this is to be understood. Suppose the particle went in a path like that. So you are dividing this path into small displacements. This is the first displacement, this is the second displacement, this is the third displacement, fourth displacement, fifth displacement. So like this you are dividing this whole path into many infinitesimal displacements. Now you want to add all of them. How do you add displacements? By using either triangle law, or if there are multiple displacements, you will use polygon law of vector addition. If you see here, all these displacements are kept head to tail. At the head of first displacement, there is tail of second displacement. At the head of second displacement, there is tail of third displacement. At the head of third displacement, there is tail of fourth displacement. So all these are kept head to tail. So the sum of all these displacements is a displacement joining the initial to final, like that. That will be the sum, because you are adding them vectorially. That will be the net displacement. So you have integral ds bar gives you net displacement, which is shown by the straight line segment with the direction as I have shown. So you can write this as S net. So this work done by a constant force becomes F dot S net. It's not a general definition. This works only if force is constant. General definition is always this integral F dot ds. But if force is constant, you can write it as F dot S. Now this further you can write it as, if I write it here, work done by constant force, you wrote it as F dot S, S net. So you can write it as F S net into cos theta, because dot product, that's how you look at it. So you take the constant force, you take the total displacement, and you find the angle between these two vectors, between the total force and total displacement. You find the angle and multiply by cos of that angle. You can interpret this in two ways. One way of interpretation is you can write F cos theta into S net. Other way of interpretation is you can write F into S net cos theta. F cos theta is component of force along displacement. See, suppose if my force, if I show with a red line, my force is like that, let us say. Suppose this is my force. It's a constant force. It has always been acting in that direction and same magnitude. Along with this force, there may be other forces which I am not concerned. I am only trying to find work done by this force. And I know the total displacement, so I know angle between them. If you see F cos theta, this term, it is component of force along displacement. So this is component of force along displacement that you are multiplying by displacement. So you can interpret this as this whole term as component of force along displacement multiplied by displacement. That's one way to look at it. So you take component of force along displacement, multiply it with displacement. Or there is other way. You look at this term S net cos theta. This is component of displacement along force multiplied by force. So this is component of displacement along force, and that is being multiplied by force. So either way you can interpret it. So work done by a constant force, you can say it is component of force along displacement multiplied by displacement, or component of displacement along force multiplied by force. So that is how you calculate work done by constant force. Let us try to see one example. Suppose I have an inclined plane. Something like that, and let us say there is a block on this, mass m. There is mg, which is a constant force. Why? Because for small heights we are assuming that the value of g is 9.8, it's not changing, and this force is always vertically down. Okay, so we are assuming that it is always vertically down. If you go from north pole to equator, obviously force direction will change. But if you go in your room, if you walk in your room, force direction is constant. Okay, now let us say the height at which this block is there, this height is h. So this height is h and this angle is theta. Suppose the block by sliding came down till here. It came by sliding. So we have to find work done by gravitational force. Now, for the purpose of this example, because this is happening in your room, gravitational force is taken to be constant because g will not change in the room. It is more or less 9.8. Direction of mg is also vertically down. So you can assume this to be a constant force as far as the experiment is done in, if the experiment is done in your room. So this is a constant force. Of course, if you take an inclined which extends from north pole to equator, such a big inclined plane, then whatever I am saying is not correct. Then mg will not be a constant force. There are many factors which affect g. Now here we have to find work done by gravitational force. It's a constant force. So there are two ways. First of all, see the displacement of the block. I will show it with blue color. The block's initial position is here block's final position is here, so it's a line segment joining initial and final. So this happens to be displacement of the block, direction is like that. So because it's a constant force, there are two ways you can do it. You can say first method is method 1. You can write magnitude of force into magnitude of displacement into cos of angle between them. Angle between them is 90 minus theta. You can write like that. This is work done by the force. Fs cos theta. F dot s na? F dot s you can write as Fs cos theta. So mg s sin theta, because cos 90 minus theta is sin theta. S sin theta happens to be h. So this is the answer, because sin theta is opposite by hypotenuse, h by s, if you construct the triangle. The other way to look at it is force is mg multiplied by displacement in the direction of force. You see, you can split the total displacement into two parts. The total displacement shown by blue line can be looked at as a vertical displacement like that, followed by horizontal displacement like that. Okay, so and this angle is theta. So this angle is theta, and of course this height is h. So force is mg. You are splitting this displacement into vertical and horizontal. Force into displacement in the direction of force. Displacement in the direction of force is vertical displacement, which is directly h, because h is the displacement in the direction of force. Okay, force is vertical, so you must take vertical displacement directly. That is the work done. No need to do anything. So I am using here force multiplied by displacement along force, or you can also do displacement multiplied by force along displacement, which is mg sin theta. Of course s sin theta is h, so it comes out to be mg h only. Okay, anyway, whichever way you do, but sometimes you can do it by inspection. Force into displacement along force is sometimes very powerful. Simple method. Force is mg, displacement along force means displacement in vertical direction is h. It came down vertically by h, so mg h is work done by the force. Simple, directly. So this is for a constant force. Whatever I have said here, this is for a constant force. Now this is special case 1, which I discussed. If you go back, general definition is integral f dot ds. I am working with special case 1 where force is constant. Then work done by the force is f dot s, which you can expand as fs. F into s cos theta you can write like that. That means force into displacement along force. Or you can write f cos theta into s also. Displacement multiplied by force along displacement. Whichever way you write, the final answer is going to be same. This is our first special case. Second special case is very interesting one. So let's look at the second special case. Special case 2. Special case 2 is general definition. First let's write it. It is integral f dot ds, where ds is displacement of that point where force is applied. This is the general definition. Now special case 2 is where f is perpendicular to ds always, not at one moment. Always. That means the force is perpendicular to the infinitesimal displacement at every moment. Then what happens? Integral f dot ds becomes integral, because the angle between them is 90, they are always perpendicular. It will be f ds cos 90, which will be 0. Cos 90 is 0. If you add those, the answer will be 0. So if force is perpendicular to infinitesimal displacement at every moment, not at one moment, at every moment, then work done by such a force will be 0. It means, so this statement implies force is perpendicular to infinitesimal displacement at every moment, not at one moment, at every moment it is happening. One of the best examples that I can give you for this case is a body moving in a circle, and I told you whenever a body goes in a circle there is acceleration towards center, or there must be a force towards center. So you see the force and the displacement ds at that instant, they are always perpendicular. When the body comes here, again displacement, the little displacement and force, they are perpendicular. When the body comes here, again the force and the little displacement, they are always perpendicular. So in uniform circular motion, the work done by force responsible for circular motion is always 0. Responsible for circular motion is always 0. Means that force is not doing work. Why? Because that force is always perpendicular to the infinitesimal displacement ds. See, force is perpendicular to velocity, because velocity is along tangent, force is towards center along the radius. So both are perpendicular, tangent perpendicular to radius. So F dot V 0, you can write V as ds by dt. That means you can write F dot ds is 0. So work done by that force is 0. So in uniform circular motion, if you can integrate it, you can go one more step and write integral F dot ds is 0. So work done by that force is 0. So in uniform circular motion, work done by the force responsible for circular motion, means which is towards center, that is always 0. I am talking about uniform circular motion. So this is special case 2. So we have two cases now. So first thing is the general definition. Work done by a force is integral F dot ds, where ds is displacement of that point where force is applied. General definition. Special cases there are two. One special case is if force is constant in both magnitude and direction, then you can write work done by that force as F dot s. And second case is when F is perpendicular to ds always at every moment, then work done by such a force is 0. So we have these two special cases. Now let us look at one example first, where all these three things are coming into picture: general force definition and special case 1 and special case 2, all will come into picture. Let's look at such an example. Suppose I have got a ball which is hung by a massless thread. So there is a thread and a small ball is hung by this massless thread, mass m, thread length is L. Thread length is L. You are applying a horizontal force F on the ball. This force is always horizontal. A horizontal force F is applied on ball, and it is slowly displaced by an angle theta. Find A, work done by tension, B, work done by gravity, C, work done by F in this process. This is the question. So let us read it once again. Horizontal force is applied on the ball. So this force is always horizontal. Okay. After the bob gets displaced, bob, or you can say ball, or I can even say bob. After it gets displaced also, the force is horizontal. After it gets further displaced also, force is horizontal only. So you are applying a horizontal force and it is slowly displaced. Very important word. When the word slowly comes in physics, what is the meaning of slowly? Suppose I ask you, what could be the speed of the ball when I say it is moving slowly? You might be tempted to give some numbers. Suppose if you say, sir, 1 meter per second, that is wrong. It's not slowly. Sir, it is 0.1 meter per second. No, that is also wrong. Sir, 0.001 meter per second. That is also wrong. Slowly means with a speed which is tending to 0. Can you give a number to it? You cannot give a number. You can only say the speed is tending to 0. Maybe if you want to over exaggerate it, not even over exaggerate, maybe if you want to be very correct, the ball moves 1 millimeter in 1 million years. Ball moves 1 millimeter in 1 million years. Means you and I here are not alive by the time we see the ball move. It is dead. We are dead. Because our lifespan may be 50, 60, 70 or whatever, 80, maximum 100. And 1 million years you have to be alive to watch the ball move by 1 millimeter. That is the meaning of slowness. Means with almost zero speed. Whenever you see, you will not see the ball moving. It is moving such slowly. So, slowly, this word means moving with speed tending to 0. This is very important point. That is the meaning of slow. That means whenever you see the ball, it is at rest. Whenever you see the ball, it is at rest. That is the meaning. Actually, it's not at rest. Okay, because after 1 million years it has moved. If it has moved means it is not at rest. But it is moving so slowly that for all practical purposes we say it is at rest. And it is displaced by an angle theta. Means it is coming to a new position, which I am showing with a different color. It is coming to a position like that. Okay, it has come to that position where this got displaced by an angle theta. In this process, you have to find work done by tension acting on the ball, work done by gravity acting on the ball, and work done by F, the horizontal force acting on the ball. This force F is always horizontal only. Okay, the direction is horizontal. What about the magnitude? We don't know. It may be changing, it may be not changing. We have to investigate that. My take is magnitude of F is changing, because as the ball climbs up, it requires even greater force to hold it or to take it by upward by small distance. So magnitude of F keeps increasing. So F is not a constant force. At least I can visualistically say that. So visualistically F is not constant force. Direction is constant, but the moment ball goes up, you need even more force to keep it going up. Okay, that is what at least we can feel, but we'll explore that mathematically. So we want to find work done by tension, work done by gravity, work done by F, these three things. And there is also a last bit, final bit, D bit. Find work done by all forces. Work done by all forces by the time it gets displaced by angle theta. So let us see how to do. Now, work done by tension is 0, because this falls under a special case. Why? First of all, what is the path taken by the ball? String length cannot change, so this point of the string is fixed. The other end has to move in a circle because string length cannot change. Okay, because if you take a compass, fix one point, and with other point you try to go in a path, it will be a circle, right? As long as you don't change the distance between the arms of the compass. Not, what is that, this thing is called to draw circles in your geometry box. I think it's compass only. So so here also this point is fixed, string length cannot change. So if the ball has to move, it has to always maintain same distance from that center. We call this as center. So the path taken by the ball is circle. Now if you see, tension is always acting towards the center. Tension on the ball is always acting towards the center, the force of tension. And this goes into special case 2. That means force is always perpendicular to infinitesimal displacement. Initially tension was towards center, displacement is along tangent, perpendicular. So work done for that small displacement is 0. You take at any position. Suppose you take at this position. Force is towards center and displacement is perpendicular to that. You must take small displacement. Why you can't take big displacement? Because force is changing direction. If you take big displacement, which direction you will take for force? That's why you have to calculate work done piece by piece. So this falls under case 1, not case 1, case 2. Work done by tension is 0 because this tension force is always perpendicular to infinitesimal displacement. So this is over. So case A is over. Let us see case B, work done by gravity. Gravity is a constant force. So if you can find a displacement in the direction of force, you can get work done by gravity very easily. Force into displacement in the direction of force. So let's look at that. You have the ball here. After some time it went there. Okay. Gravity is always acting down, mg. It is always acting down only on the ball. If you see the displacement of the ball, this is the displacement of the ball, total displacement. You can split this displacement into vertical and horizontal. You must take displacement in the direction of force. In the direction means in vertical direction. Here it is opposite to force actually. So you must take this displacement. String length is L. This angle is theta. So this length is L cos theta. But this total length is L, length of the string. So this has to be L into 1 minus cos theta, but it is upward. So you see force mg is down. Displacement in the direction of force is up. So work done by mg will be minus mgl into 1 minus cos theta. Why minus sign is coming? Because force and displacement are in opposite direction. Or you can even do like this. You can write the displacement, look carefully. If you take this as x-axis and this as y-axis, force is given by mgj always, constant force. Displacement is given by, look very carefully, L sin theta I minus L into 1 minus cos theta j. What is this displacement? This length is L sin theta and it is along x-axis. So L sin theta I. What is displacement? L into 1 minus cos theta, but it is opposite to y-axis. So multiply with minus j. If you do f dot s, first term dot product will be 0, j dot I will be 0. Second term dot product will give you minus mgl into 1 minus cos theta. J dot j is 1. That's what I wrote here, the above. So work done by mg is f dot s because it's a constant force. So this is case 1. If you see, both the cases are covered now. Case 2 is covered in a bit. Work done by tension is 0 because it is always perpendicular to infinitesimal displacement. And work done by gravity is 0 because, not 0, work done by gravity is minus mgl into 1 minus cos theta by using f dot s. Now the third bit is there, work done by f in the process. Work done by f, first of all, the ball is going very slowly, means whenever you see the ball is at rest only for all practical purposes, because it is moving with a speed tending to 0, means it is practically at rest. So if you assume that the ball has turned by certain angle phi, for example, at this moment there is mg, there is tension, and there is your applied force F, and the ball is at rest, means its acceleration is 0. Because if it is moving very slowly, almost with 0 speed, it is as good as it is not moving, so acceleration is 0. So we must have equating vertical forces T cos phi equal to mg equating horizontal forces, T sin phi is equal to F. From here, F equal to mg tan phi. You see this? Means as phi increases, F increases. Otherwise, the ball will come back. It won't continue to go up very slowly. So as phi increases, as the angle increases, you have to apply more and more force to take the ball slowly up. So this is a variable force. It's not a constant force. It's a variable force. Force varies with angle phi. Force varies with angle phi. So how to find work done by this force? You must use, if it is a variable force, you must use integral F dot ds. So this is the force at some intermediate position when angle is phi. Initially phi value is 0. Finally phi value is theta. Finally phi value is theta. Okay, so phi is a variable whose value keeps changing. Initially it is 0, finally it is theta. So I took an intermediate position where the angle is phi and the force is mg tan phi, it is horizontal. How is the displacement? Displacement is along tangent. That is the displacement. Suppose in this displacement it makes a further angle d phi. Then this displacement you can consider it as an arc or as a straight line also, because it is a very small angle. So if you consider it as an arc, see, this is the bob. It already moved by phi, a very big angle. Now it is further moving by a small angle d phi. It moving in an arc. Arc length is radius into angle. Radius is L, angle is d phi. But you can consider this arc length as straight length only, because it is a very small angle tending to 0. So the little displacement is L d phi. That is the little displacement, ds. So force is mg tan phi. It is horizontal. Dot product with ds is L d phi. It is not horizontal, it is tangential. What is the angle between this tangent and the horizontal? Let us explore this carefully. Ball was here. It went by an angle phi. This is the tangent and small displacement ds is there. That displacement subtends an angle d phi at center. If you need, you can write that. Force is like this. What is this angle? Angle between force and that little displacement. This is 90. Okay, this is 90. Let us drop a perpendicular here. So if I try to draw this diagram better, let me try to draw this better. Look very carefully. This is going in a circle. This is force. Okay, displacement is in that direction, tangent. If I drop a perpendicular here, tangent and radius make angle 90. We want this angle theta between force and displacement, or I will say alpha. This is 90 minus alpha, because total has to be 180. So this is alpha, or which is nothing but phi. Okay, so once again let me show you what I am saying. If this angle is phi, this is 90, this is 90 minus phi, total is 180, of which 90 is gone. So this plus this angle must be 90, so this must be phi. So angle between the force and displacement, force is horizontal, displacement is like that, this angle is phi. So when you do dot product, what you will get here? Integral mg tan phi, that is force, magnitude of force into magnitude of displacement into cos of angle between them. That is what you are getting here. Okay, when you do dot product, force magnitude is mg tan phi, displacement magnitude is L d phi, but force and displacement are not in same direction. See the arrows, there is an angle of phi between them, so into cos phi. So I am using general definition integral f dot ds. You have calculated f at an intermediate position and you are finding little displacement in that position only. So at intermediate position, the string makes phi angle with vertical. If you give a small displacement, it makes further angle d phi. In calculus, you always take like that. After an angle phi, you take an angle d phi, or after a distance x, you take a small change in distance dx, or after a distance y, you take a small change in distance dy. Similarly, after moving by phi, it further moved by d phi. Okay, so the displacement in that further movement is L d phi, force is mg tan phi, and angle between force and displacement is phi. So work done is integral f dot ds. It comes out to be, okay, integral f dot ds, work done by that force happens to be integral f dot ds. Force value at some intermediate position we got it as mg tan phi. Displacement we got L d phi. Angle between force and displacement is phi, so you should write cos phi, because when you do dot product, cos of angle between them you should write. And phi is ultimately going from 0 to theta, because ultimately phi will change from 0 to final angle is theta. That is what phi is. So tan phi into cos phi is sin phi. Sin phi integral is minus cos phi. So minus mgl integral, mgl integral sin phi d phi 0 to L. This is what you are getting. Is it right? Tan phi into cos phi, sin phi. mgl is a constant. mgl is a constant. And integral sin phi is minus cos phi. So minus mgl cos phi, and limits are from 0 to theta. Put upper limit, it will be cos theta, lower limit will be 1, but there is already a minus sign, so it will be mgl into 1 minus cos theta. This is work done by F. So you see, I have got all the three. Work done by tension is 0 in this process. Work done by mg is minus mgl into 1 minus cos theta. Work done by F is plus mgl, that's what I got, into 1 minus cos theta. Something very strange, if you see, if you add all these, total work done is 0. This is very interesting. We will explore this later. We have work energy theorem. If there is work done by all forces, kinetic energy must change. But in this example, kinetic energy is not changing because it is always moving with 0 speed, almost 0 speed, very slowly. So kinetic energy is not changing. So work done totally must be 0. Okay, but we will explore this at a later stage. Why work done by all these forces should be 0? Because if it is not 0, kinetic energy should have changed. When all people do work, something must happen. Either speed must increase or decrease. Or if they all together do 0 work, speed will not change. So here all are doing together 0 work because speed is not changing. Speed of the bob, it's moving very very slowly, almost with 0 speed. So work done by all these forces is 0. So work done by tension, it is special case 2. Work done by mg, it's a constant force, so special case 1. Work done by F I did by general definition, by integration, because F is a variable force. So all the three parts are taken care here in this example. All the three parts are taken care. See, in your lower classes, you learn about an example. A person is keeping a heavy object on his head, let us say suitcase. There will be porters in railway stations who will help you with your baggage or luggage. So they will be putting a suitcase on their head and they will be walking. So question is, what is work done by the person on suitcase if he moves by distance L in a straight line? He has moved a distance L. Mass of suitcase is M. What is the work done by person on suitcase if he moves a distance L. So what do you think is the work done by the person? Just type in your answers. Okay, just type in your answers. What do you think is the work done by the person on suitcase if he moves by a distance L? Zero. Aarti says 0. Shrenika says 0. This is a standard example in lower class textbooks. 0. But this is wrong answer. Okay. First of all, let us see what are the forces the person exerts on suitcase. On suitcase, person exerts a normal contact force because he is in contact with the suitcase. And person exerts a friction on the suitcase because he is trying to take the suitcase forward. If friction is not there, what happens? If he keeps the suitcase here and if he walks, he will go forward and suitcase will just fall here if friction is not there. So person is definitely exerting a frictional force on the suitcase. So normal contact force is exerted by person, friction is exerted by person, and there is a displacement L. Of course, normal contact force will not do any work because the force and displacement are perpendicular. But what about friction? The friction on the suitcase is doing positive work. Work done by friction, because the frictional force on the suitcase and displacement. In fact, the suitcase is moving forward because of friction only. Friction is doing work. So, if you say work done by the person, means work done by the forces exerted by person. He is exerting two forces, normal force and frictional force. The normal force doesn't do work, but friction does work here, which is the reason why we see a stationary suitcase starts moving as he starts walking. So work done by the person is not 0. It will be static friction value. We don't know what is static friction value. That you must get by applying Newton's laws. If you know the person's acceleration and things like that, I can calculate into displacement L. Because the static friction and displacement are in same direction, there is no cos theta. They are in same direction. So you see, the work done by person on suitcase is not 0. Work done by the normal force of the person on suitcase is 0. But work done by the frictional force the person exerts on suitcase. Who is exerting frictional? His head is exerting friction on suitcase. There is a reaction of friction by suitcase on his head also. So friction, there are two parts. One is acting on suitcase in forward direction. The other is acting on his head in the backward direction. This is static friction. So definitely the person is exerting static friction on suitcase, and that is doing work because there is a displacement for suitcase. Now one thing you should keep in mind, work done by a force is frame dependent. Work done by any force, this depends on reference frame. Please be very careful. Even if it is inertial frame, work done could be different. For example, you see, for a stationary person, suitcase is moving by distance L. For a stationary person. So there is work done by friction. But for this fellow, what is displacement of suitcase in his frame? 0. Displacement of suitcase in his frame is 0. So there is no work done by friction for him. But for a ground observer, there is work done by friction. So you see, it depends on frame of reference. I'll give a simple example, another example. Suppose if I have a car and which is accelerating, let us say, I am sitting in the car and beside me there is a heavy box on the seat. Car is accelerating. For me, there is no displacement of the box. It is at rest with respect to me. So according to me, even if there is friction acting on the box, work done by friction is 0 because there is no displacement. But for an outside fellow, friction is acting, taking the box along with the car with acceleration A, and there is a displacement also. So there is work done by friction. So you see, work done is a frame dependent quantity. Later we will see the kinetic energy is also frame dependent. So our work energy theorem, the left side we will see it is work done which is frame dependent, right side kinetic energy is also frame dependent. As long as you apply it properly in inertial frames, it doesn't matter which frame you apply, it will be correct. Okay, it will be correct. For example, for the car fellow, the box is not moving, work done is 0 and kinetic energy change is also 0, it is at rest with respect to him. But for outside fellow, there is work done by friction on the box, and because it is accelerating, there is also change in kinetic energy, and if he applies work energy theorem, he will also get it correct. So we will see work energy theorem later, but these are all very important points. So the most important point is work done by a force is frame dependent. Work done by a force is frame dependent. It depends on the frame of reference. If you change the reference frame, the work done by that force may be different. But keep in mind, real forces, I am not talking about pseudo force, real forces, they are frame invariant. Whichever frame you go, force will act definitely. Real force. I am not talking about pseudo force. Suppose if friction is there for car observer, friction must also be there for ground observer. Is it clear? Because force, as long as it is a real force, it doesn't matter which frame it is in. Force is there. Of course, pseudo force, it depends only on, it comes only in non-inertial frames. That's a different issue. It's not a force in strict sense. Pseudo force is a fictitious force. That's why we use the word pseudo. But all real forces, they are frame invariant. Whichever frame you go, force is still there. If you say one observer saw that there is force of 5 Newton, a real force, every observer sees that 5 Newton. But they may see different accelerations or different speeds because they may be moving. That is a different issue. So work done by a force is frame dependent. It depends on frame. But force itself is frame independent. What about displacement? Displacement depends on the frame. Okay, so work done, even though this is frame independent, as long as it is a real force, this depends on frame, and hence work done also depends on frame. This you keep it in your mind. This is a very important point. Very important point. So up till now we have seen the basic definition of work done by a force. Okay, the most general definition and all the special cases. Now the next topic which we want to do is, there are special class of forces which are called conservative forces. Conservative forces. These are special class of forces. So I want to talk about these forces in the coming lecture. We'll do it after the break.